Okay, I think let's get started. The clock has ticked up to the top of the hour. My name's Roger Riggs. I work in the Java Products Group in the Core Libraries team, and I've been with Sun for, well, not Oracle, for quite a number of years. The last several projects I've been working on is the date and time API, and I embarked on a project in cooperation with a bunch of other people to add some resource management support to support some initially closed applications in the JDK. So this is a talk about the infrastructure and the techniques that we use to gather tracking statistics about resource use and how it might be used. So real quickly, some goals, a bit about the model of the API, some examples of measuring and monitoring, the techniques we used in the instrumentation, and some bits and pieces about how it might be applied if you were writing a policy mechanism to go with it. So from the outset, the part that we envisioned and we implemented for use in the JDK was all mechanism, no policy, because it's pretty easy to separate the mechanism from the policy. We're just trying to count resource uses. This is things like, socket opens and file opens and byte usage. There are a few enforcement mechanisms that will get that to just be able to say we might need to be able to throttle the resource usage or deny it. Mostly, we expect the thing to run kind of open loop in terms of the tracking mechanisms. Performance, a key goal was that it had no performance impact whatsoever and not be visible if it wasn't in use. And that when it was in use, it had a very low overhead. The goal was 5%. We actually beat that by quite a bit. We'll get to that toward the end. So the resources that we wanted to be able to track were the typical library ones: files, sockets, file descriptors, datagrams, threads, CPU, and one of the most interesting ones is heap. In particular, retained heap usage, not just how much memory you've been allocating, but how much you're still using. And typical metrics of open and closes of things like sockets that have to match, and then bytes read and written. So typical use case is something where you've got a lot of activities going on inside of a server. You really could use a way to know what resources are being used by each of the tasks that's going on in the server. And you want to develop it either, for a couple of uses. You either want to develop a model of what a particular task or group of threads is using so that you could predict how much it's going to use for a particular incoming service request. And at a higher level, you might want to use it for some kind of load balancing or control over injecting new work into the system. And at the limits, you want to be able to also be able to monitor whether some of these tasks are either using too much resources or they're really sort of going way overboard and track them that way. So the model for the resource model is this is a resource context, pretty straightforward thing. Consists of a set of threads that are using resources and are contributing to the meters that are counting resource use within the context. As activities go on, whoever is supervising the tasks is binding and unbinding threads to the resource context. And that punches down through also into the VM elements, as we'll see a bit later. Threads are the things that use resources. They open files, close files, allocate heap, etc. Resources are requested and released. Open is the request and release is the close. Some of them are not symmetric. When you're reading a file, typically you just say, I want to read 10,000 bytes or a gigabyte or something. Though there is a use case there to get accurate numbers of releasing data. If you tell it to read a gigabyte and really there are only 1,000 bytes of input, you want to make sure that the counts are accurate, so it'll only read 1,000. And as part of it, the requests can be approved by the policy mechanism, denied, or there's a lightweight throttling mechanism that can slow the approval to use resources. Within the resource context, there are meters that accumulate sort of net resource usage, the requests minus the releases, and also sort of total usage over time. So if you want to know how many bytes have been totally requested or how many files have been opened, that's a separate count from the current net number of files that you have open. The basic mechanism sort of at every point is at the point a resource is about to be used, the current thread is mapped to the resource context, and then the type of resource is mapped to a particular meter within the resource context. The resource context is a pretty simple interface. It's got bind and unbind of threads. You can get a list of the threads that are bound to the context. You can add meters, resource meters, of which we'll get to particular subtypes, list the meters that are in there. And then one of the key operations is this get resource request is an operation which finds the correct meter for the particular type within a resource context to add or modify. And then the request accurate update is a feature that was added in particular for the heap, where we'll get to this a bit more, but with the dynamics of garbage collection, sometimes you want more accurate information than is currently available, just as the garbage collection normally cycles. And then to get to the resource context, you need a little bit of a factory to create, look up, and find out which context exists, to map the current threads to the right context, and to do some other housekeeping. There are two sort of special contexts that exist. There's a totals context, which lists sort of a sum of all resource usage of all contexts that exists. And then there's an unassigned context, which is used for all threads that are not otherwise bound to a particular resource context. It's sort of the catch-all, so that it simplifies things if there's always some resource context, which can be dispatched to account for resources. Resource management can be enabled, and you can ask which supported types are supported. We'll get to some other details in a bit. So here's a real quick sort of, if you were writing an application to measure some resources, you end up getting the current resource factory. You can create a resource context. This one just adds a simple meter for file opens and file reads, and they're added into the resource context. It binds the current thread to the resource context, and then, does something. The meters are updated essentially all the time, continuously, so immediately and at any time you can ask, this is the total allocated is the total number of files that have ever been opened. And since this is the bytes read, means it's the current number of bytes that have been read on that meter. So the API is pretty simple to use at a high level. There are a number of different kinds of meters that are useful to keep track of what's going on. The simple meter just counts. It counts the net usage and total usage. One of the more useful ones is a notifying meter, which counts, but it also will call back to the resource approver through the resource approver interface that's been registered with the current value that's being requested and the previous value. And we'll see a bit more of that in a minute. A couple other simple meters added into the set were the bounded meter that provides an upper limit on the bound of something. It's sort of automatically enforced even without a callback. Just says no when you get to the limit. And the throttled meter is a little more interesting. It actually keeps track of how much has been used over time, and you can set a limit, and it will delay approving some requests until you're back under the resource limit. I mentioned the resource types that are supported. Some of them are in the libraries, and the more interesting ones, sort of technique-wise, are in the heap. There are a couple of edge cases where it's really nice to be able to know what resource is actually being opened. So there's this resource ID concept, which will give you the name of the file being opened. In the case of threads, should give you a little information about the heap. And it also includes information about the accuracy of the particular measurement, which comes into play when we're talking about the garbage collection and the retained heap. So Simple Meter has a really simple interface. It's got methods to get the current value, the total value, the type. The request is sort of the operative method that when a resource is being used, it calls the meter and say, I want to use this much, use or release this much. If the amount is positive, it's a request. If it's negative, it's a release, and the resource ID. The part of actually counting is fairly fixed in the infrastructure, so the methods are final. But in order to allow sort of modifications in different behaviors from the meter, this validate method can be overridden with a, so it's passed the previous amount, the amount that's being requested, and the resource ID, and the subclasses use that to modify the behavior of the meter. So this is extensible if you have some other clever behavior of the meter that you'd like to add. The implementation of the meters is pretty straightforward, though after the discussion of long adder, maybe I should have used that instead of the atomic long counters that are there. But we don't expect to see a lot of contention in the meters because they're usually used by different threads at different times. The usual bit of details. One of the things that's interesting throughout this whole process is that since exceptions can get thrown at various points in time, you always have to be aware of how to keep the meters, have the correct value even if some exception is thrown something. For example, if when the resource approver is called to say, can we allocate this amount of memory, it may throw an exception, and the counters still have to be kept reasonably accurate in that case. A second example, sort of similar to the first, if you wanted to have a callback when resources are allocated. Here, I'll show on the next page the particular method that can be called. It creates a notifying meter with this as the callback monitor. The rest of the code pretty much looks the same. The resource approver callback is, it's fairly straightforward. It gets the current meter, the previous value, the requested amount, and a resource ID. And then it can decide whether how it's going to deal with allocation or deallocation, logging it or accumulating it. One of the things that we've ran into and got stumbled over a couple of times is that since this is called back from inside of sort of every I/O operation, you have to be very sensitive both because of performance impact and the potential for recursion. For example, you might think, oh, well, we'll add a printf in here. Well, writes to standard out are also part of the resource management system, and the thing could quickly recurse. Now, we did separate out standard in, standard out, and standard error as different resource types so that it would be a little less easy to bump into this. But the biggest caution here is that the performance impact of putting something in the callback, because, for example, I hope nobody's really calling a file input stream to read it one byte at a time, but if it did, the resource management overhead of that individual byte call would be much higher than anything you'd expect. So that's kind of the framework and everything. The other interesting piece of it, maybe more interesting and was a bigger part of the work, was the instrumentation that's required to actually call into this framework. And there are two types, synchronous types that are done by out of the library, and which is done by essentially using JVMTI and bytecode injection into the right classes. And then there's an asynchronous section of things that have to be polled because of the way they're used. So on the library side, we had the benefit of using some template infrastructure that was built for JFR, where we can write the templates in as a Java class. It's applied by a mechanism that wraps the method in the template around the original method in the class. And so it's pretty easy to write a template from the structural point of view. So the templates are applied the first time you use it. So until the first time somebody uses resource management, there's no code, there's nothing injected into the classes. The templates, as I mentioned, they get wrapped around the target methods, and I'll show an example in a minute. There are sort of annotations specific to this templating mechanism that are used to identify the target methods in the target class, and some other special cases where, since you want to the desirable feature is to be able to compile a template class normally, but because of access roles, in fact, it may be it's a little bit more severe with modularity coming. You can't just refer to everything that the implementation class that you're trying to annotate can access. So there's a couple of special cases there. And as mentioned a couple other places, since they're wrapped around the method, so the original method is inlined into the template and then redefined. ASM is used to do the bytecode munching, and then JVMTI is used to insert the modified class. So the template mechanism is not really a general purpose mechanism. So we didn't, it doesn't handle every possible combination. It doesn't handle the exceeding class file limits. We didn't run into that anywhere. It doesn't have a way to instrument constructors. And one of the biggest things is that would have been nice would be a way to add fields, because we could have gotten some performance improvements out of it. But as with, because of the way this operates, the template code really has to be very sensitive. It's very brittle and depends a great deal on the structure of the code you're implementing. So it's not simple, I'm just counting the entry point. It's, I have to make sure that the original invalid arguments and null pointer exceptions get thrown at the right place, et cetera. So writing the templates can be a little bit tricky in that you've got to, well, some of the structure is pretty straightforward. Before the resource would actually be consumed, you've got to find the right meter and the right type. Let's see an example on the next page. And you have to be able to deal with the exceptions that might happen as part of the original method, as well as that might have happened as part of the template code. And then after the resource is used, then you may have to deal with residual effects of the exceptions. And then another important one is that you always want the opens and closes to be balanced, so at any time the resource management view has an accurate number of how many files are open or sockets. This is too small to read, sorry about that. But it goes through the steps of, this first section here is, if it's going to throw a null pointer exception, you really want the original code to do the argument checks. So it defers to the original code. This is in file output stream. It needs to map the current thread to find the resource context, look up the right meter using the current type of file, and then it has to create a resource ID to identify the file being opened. And then you get around to the point where you can actually call the resource, make the resource request, which may fail because it wasn't allocated enough as much as requested, or it may fail because of a thrown exception. But if it succeeds, then it actually, this write down here, the way the template is structured, that's actually what calls the original write method of file output stream. And then it has to go through a little dance to make sure that it returns any unused part of the resource allocation. So some of the templates, they can get more interesting than this, but this is a simple example. There are a bunch of corner cases that show up in writing the templates and writing the instrumentation. Some of the way the APIs are implemented in the JDK aren't very symmetric. You won't find necessarily the open method and the close method in the same class. Or in the case of asynchronous I/O, the place where it starts the I/O is potentially in a different file and a different structure than when the I/O is completed. And so they get a little bit more intricate to inject and add extra wrappings around things. For threads, the assumption is that initially you can bind whoever's managing the threads will bind the thread to the resource context. Threads might spawn other threads, so the default there is that a thread that spawns another thread gets automatically bound to the same resource context. But it's a bit tricky, of course, because the thread object that's created to the Java side doesn't immediately cause a OS thread to be allocated in it to run. So there's a little bit of an extra dance there. And then there's some cases where the model for requesting a resource is such that you really should know the resource ID so you can call it back when you're making the resource request, but you don't know what it is yet. So in socket accept, for example, until the accept actually completes, you don't know what socket's on the other end of the connection. You don't even know the local information. So in that particular case, it sort of optimistically accepts the connection, and then if the resource management says no, you can't do that, it closes it down. So it's a little bit of a fiction, but typically, you know, the way that we expected this to be pushed into existing applications was that sort of normal operation was what drives the whole system. So just some interesting things. So on the other branch of the instrumentation has to do with asynchronous events. The biggest, most interesting one to the WLS folks that got us started on this project was the use of retained heap, and we'll talk about that in a minute. The other two metrics about allocated memory and CPU, they both have to be sampled because there's no good place to hook in a synchronous hook. So there's a background thread that monitors those things at a period, and it does the corresponding lookup to get the information back into the resource context in the right meter. I had a lot of, actually, I didn't do any of the work on the G1 collector. I had help from, they did the work. But instrumenting the retained heap is implemented in the G1 garbage collector. G1 was a good match for what we're trying to do with resource management because it did allocation within regions, and there was a very straightforward mapping to say that all the objects for a particular resource context would be allocated from a single region, and that the other GC mechanisms would maintain the invariant that within a region all the objects were bound to the same resource context. And there was a little bit on the VM side to add the VM's idea of what a resource context would be, and associate that with both the threads. You could bind a resource context to or a thread to a resource context in the VM's view of the world, and to propagate that through as the resource allocation was going on within the regions. One minor point was that at the time you bind a thread to a resource context, it has to allocate a new thread local allocation buffer to make sure that all the objects that are allocated from that point on are associated with the right resource context. And then at the tail end of destroying resource contexts, all the memory that used to be held by that, some resource context has to go somewhere. So it gets, they all get sort of moved en masse to a different, another resource context. There is sort of a magic system resource context, which is used as a dumping ground for everything that's not otherwise bound. So the garbage collector maintains this information about allocations and regions. And as the GC phases complete, it generates the events that are sent up to the a Java thread that's monitoring the behavior. And it retrieves the information from the GC and passes it off to the appropriate resource context. That all is pretty straightforward. The different GC phases in G1 have different sort of accuracies. If you don't do a full GC, you sort of don't know really how much retained heap is attributed to a particular resource context. And that, we had a lot of discussion about how to deal with the, I don't want to say the inaccuracy, but the varying accuracy of information about what's in the heap. So in using the API and using the resource management, the information you get out of the library resources are pretty clear-cut, synchronous model. The numbers are accurate as it happened. In the case of heap allocation and retained statistics, the whole thing's pretty dynamic, as probably most of you are very well aware of. So if you're trying to write some policy mechanism on top of this, it's hard to say that that particular task has reached a limit and should be, should somehow be disciplined, more disciplined in its use. You really don't, even though it seems natural to say, well, if somebody's getting close to the limit, I should do a full GC and make sure I got completely accurate numbers and know so they aren't violating whatever constraints it is. But full GC is sort of a dirty word, right? Nobody wants to spend the time to do that because it's both delay and slows things down. So in terms of writing policies, you need to find a way to deal with much less accurate information as things go and build on trends over time and the behavior. And that also helps you, since our goal was sort of the normal operating, sort of providing information to enhance the normal operating behavior of the runtime. You really want to build trends and move more slowly than just simple actions. So it all has to be done sort of dynamically and be smoothed out over time to get good behavior. As I mentioned earlier, there are quite a number. This is a fairly sensitive API because it gets called. The callbacks can happen in the middle of everything. It is protected by both a command line switch to enable the resource management and a security manager permission to enable it and actually to use the resource context. Performance, as I mentioned earlier, the performance hits can be problematic because of the level of injection that you're doing. And you also have to worry about, since the callbacks happen from inside the I/O code, it may happen at a protection level or in a protection domain, which is which is trusted in a way that you wouldn't expect. I mentioned these other caveats about worrying about recursion and being very sensitive to what you're doing in the callbacks. So when you develop, if someone could build a policy engine on top of this, they have to be a little bit sensitive to these issues, including that the mechanism does have a way to deny usage of something, and the exceptions get thrown, for example, in I/O as I/O exceptions. Most applications probably know how to deal with that in some way. They're probably likely to fail what they're doing, but they won't have sort of Byzantine failures. There was, in the asynchronous side of things, there's no mechanism to deny or throttle heap usage or CPU usage within this mechanism. We spent a lot of time talking about, what would happen if you started throwing out of memory errors, or if you denied some set of tasks, either CPU time or memory, and all of them seem to go, total upside down in a hurry. So because we don't have thread.stop, you can't really stop things from the bottom. So if you want to build a policy mechanism that's going to terminate some behavior, it's got to do it from its other mechanisms in terms of not starting new work or denying things. It all falls back to this thing. So there's no good way to tell an application arbitrarily, just stop. There's no safe. Anyway, so the best mechanisms for control are sort of back at the top of at whatever system that's controlling the workload. So in our measurements, which we haven't gotten to final numbers under real circumstances, but in one spec JVB, we measured the overhead as being under 2%. It depends, obviously, quite a bit on the mix of CPU and I/O activities that are going on. It's fairly easy to do the instrumentation because of the templates. We don't have to deal with JVM PI and ASM, at least at the level that I was able to work. by reusing these mechanisms. And the complexities of developing a policy on top of this shouldn't be minimized, because the information that you get is not really cut and dried in terms of what you should do and how you should operate how you want your system to operate. All right, I had quite a bit of help from the Hotspot JC team, Stefan Johansson and John Coombs. Stefan Larson from the serviceability team helped with the JVM TI and the templates. One of my colleagues, Brian Burkhalter, helped with the IO Instrumentation, and Charlie Hunt helped us with the performance things. And so that's what I have to say. Questions? Yes?
First of all, I don't understand, is this going to be a standard Java API as part of OpenJDK? Is it an Oracle-only thing? Is it going to be part of Java 9?
Right.
What is this API?
So this is not part of OpenJDK. It is an Oracle commercial feature. It was originally implemented in it's implemented in 8U40, and
it's already part of the Oracle.
It's part of the Oracle JDK. It requires command line switches to enable the commercial features and the resource management.
Yeah, under the same terms as JFAR?
I want to say yes, but I don't remember exactly the terms of JSR. It is a commercial feature. It's covered under the same, I believe it's, for research and educational use. Right.
But here it's actually an API, so it's taken out of production.
Right. It is documented separately from the OpenJDK APIs and with the disclaimer on it. So, others? Okay, I'll be around if anybody has questions. Thank you.